Good day, everyone. Today, I'll be discussing protection devices, alarms, and shutdowns in combustion control and fuel systems. These systems are critical for ensuring that boilers and turbines and board ships operate safely, efficiently, and reliably. Throughout this presentation, I'll explain what each system does, how it works, and why it plays a vital role in marine safety. Three systems that work together. Protection devices. Protection devices prevent unsafe operation by automatically regulating equipment. Alarms. Alarms early warning that alert me to potential problems. Shutdowns or trips. Shutdown or trips final safety actions that stop the system to prevent serious damage. First, protection devices constantly regulate the steam and fuel to keep the system operating safely. If something begins to go wrong, alarms alert me early so I can take corrective actions. If the situation becomes critical, shutdowns automatically stop the equipment to prevent catastrophic failure. Protection devices are automatic controls that regulate boiler and turbine operations to prevent unsafe conditions like overspeed, overpressure, or flame instability. Protection devices act as the system's guardians. They monitor important parameters such as steam pressure, turbine speed, and fuel flow. When these parameters start moving toward dangerous levels, the devices automatically adjust operations to bring them back to safe limits. Main steam valve control. Purpose: control the flow of steam leaving the boiler to propulsion turbines or auxiliary systems. Operation: automatic or manual. Importance: prevent sudden steam surge that could damage downstream equipment including turbines. The main steam valve control manages how much steam leaves the boiler. While it can be operated manually, it's usually automatic responding to changes in system demand. Careful steam regulation prevents dangerous pressure surge that could damage equipment connected to the boiler, like turbines or auxiliary systems.
The control valve receives a signal from a controller, such as a PLC or a DCS, in order to operate. The controller compares the actual flow rate to the desired flow value, called the set point. The controller will produce an output to move the valve to bring the flow rate to the set point value. A control valve is a power-operated device used to regulate or manipulate the flow of fluids, such as gas, oil, water, and steam. It is a critical part of a control loop and is an example of a final control element. The control valve is by far the most common final control element used in industry today. A control valve can be operated electrically, pneumatically, or hydraulically. A control valve receives a signal from a controller, such as a PLC, in order for it to move, resulting in a change in flow. Because the PLC signal is electrical, the control valve may require a device to convert that electrical signal so that it can operate. A control valve has two separate components: the valve and the actuator. Valve bodies are of different types or styles depending on service conditions, piping layout, and desired application. The two classes of control valves are linear motion and rotary motion. On a linear motion valve, the stem and valve movement is up and down. A common type of sliding control valve is the gate valve. A rotary motion valve, in almost all cases, rotates 90 degrees from open to the closed position. A commonly used rotary valve is the butterfly valve. The actuator is the device connected to the valve through the valve stem that provides the force required to move the valve. As we said earlier, the actuator can be controlled electrically, pneumatically, or hydraulically. The most common and the most reliable is the pneumatic actuator. The control valve receives a signal from a controller, such as a PLC or a DCS, in order to operate. The controller compares the actual flow rate to the desired flow value, called the set point. The controller will produce an output to move the valve to bring the flow rate to the set point value. Because of how pneumatic actuators are built, a control valve will fail to a specific position when a loss of the control signal occurs. As the supply air pressure is increased, the rubber diaphragm pushes against the spring and moves the valve stem down into the valve body. As the supply air pressure is reduced, the spring will move the valve stem out of the body. The position to which the control valve is moved, if a loss of signal occurs, is referred to as the failsafe mode. The type of failsafe mode depends on the application for which the control valve is used. The actuator causes the valve to close in a fail-closed control valve. The actuator causes the valve to open in a fail-open control valve. In normal operation, the force of the spring must be overcome by the electrical or pneumatic actuator. In the event of a power failure to the actuator, the electrical or pneumatic force is no longer present, and the spring pressure forces the valve to open. You might wonder how much the valve opens or closes when the flow rate changes. Well, that depends on a number of things, such as the percentage of flow rate change and the diameter of the pipe. Regardless, the controller must be tuned so that it produces the correct response to any change in flow rate. This is most commonly achieved by using PID control within the PLC or controller.
Speed override controller. Purpose: prevent turbine overspeed when steam from the boiler drives it. Operation: cuts or limits steam flow if RPM becomes too high. Important: one of the most dangerous situations is a turbine is spinning too fast. The speed override controller automatically takes over if the turbine's RPM exceeds a safe limit. It immediately cuts fuel or steam to slow turbine down and prevent catastrophic damage like a burst or shaft failure. Boiler pressure controllers. Steam drum pressure control. Maintain safe steam drum pressure. Safety relief valves. Automatically release steam if pressure rises above limits. Maintaining steady steam pressure is essential for safe and efficient turbine operation. These controllers make sure that both the inlet and outlet steam pressure stay within proper ranges. This protects the turbine from pressure swings that reduce performance or cause dangerous vibrations.
A pressure relief valve is designed to open in order to relieve excess pressure and then to close once pressure conditions have returned to normal. They can be classified either by rapid opening or by a speed proportionate to that of the opening pressure.
In normal operation, like in a gas pipeline, the disc stays seated, holding the system below the set pressure, let's say 4 bar. Rising pressure, when pressure in the pipeline rises beyond 4 bar, for example due to a blockage or pump failure, the disc lifts off the seat, opening the valve to prevent disaster. Pressure relief, excess gas or liquid escapes through the outlet port, safely reducing the system pressure. Reseating, once pressure drops back to a safe level, below 4 bar, the spring pushes the disc back into position, sealing the system until it's needed.
Load controllers and combustion regulation. Load controllers adjust fuel and airflow to match steam demand. Importance: prevents overfiring and ensures efficient, stable combustion. The load controller automatically balances how much fuel I burn based on how much steam the system needs. At the same time, steam extraction controls divert steam to other ship systems, such as heating and auxiliary equipment, without compromising turbine performance. Extraction override and manual control. Override controllers prevent unsafe steam withdrawal for auxiliary systems. Auto manual stations allow me to take over if automation fails. Some steam produced by the boiler goes to auxiliary systems like heating and fuel heating. Override controllers make sure that these extractions don't reduce boiler pressure below safe levels. And if automatic controls fail, I can switch to manual mode to keep the boiler safe and operational. Alarms. Alarms act as early warning systems that detect potential issues before they become critical. They alert operators when conditions deviate from safe ranges, allowing corrective actions to be taken. This proactive approach helps prevent the activation of protection devices or shutdowns, ensuring continued safe operation. Types of boiler alarms: low fuel pressure, high fuel pressure, high steam drum pressure, low water level, flame failure. Alarms act as a first warning system when issues like low water level, high drum pressure, or flame failure occur. Alarms alert immediately. This early warning gives me the chance to correct problems before they escalate in serious hazards. Shutdowns or trips. Shutdowns are automatic emergency actions that stop the boiler or related systems when conditions become critically unsafe. Shutdowns or trips. Examples: flame failure trip, low water level trip, high steam pressure trip, low fuel oil pressure trip, turbine overspeed trip. If alarms are ignored or the situation warrants quickly shutdowns, a trip activate automatically. For example, if the flame inside the furnace goes out, a flame failure trip instantly shuts the fuel to prevent an explosion. These shutdowns are the final defense that protects both the boiler and everyone on board.